Let's see whether I can use this guy here.
I think I can check here anyway. Which one is it? Microphone 4? 4.
1, 2, 3, 4, 5.
Yeah.
Perfect.
I will
Okay,
enable
so let's start.
So if you want, you
Today,
can enable it.
again, we have a guest
This would
presenter.
enable your. Okay.
It's Dr. George Cardoso from Huawei. He's the chief architect for planet-scale AI ops at Huawei. So Huawei actually produces clouds for the German and Dutch telecom. So that is how we get into touch. But we are also interested in automation of the operations of such a cloud, and so that is what he's focusing on. He worked before also for SAP and for Boeing in the US, right?
Yeah, many years ago.
Many years ago. And so he holds a PhD degree from University of Georgia in the US, and he's professor at the University of Coimbra in Spain, Portugal. In Portugal. And so, I think since 4 years or so, 4 or 5 years, you contribute to our lecture on cloud computing. It's a great pleasure. Welcome again. And so let's hear about OpenStack, the open source cloud environment. Okay, please start.
Good.
Organization question, yes?
Do you upload the slides?
I can do that, yeah. I do it. Mm? Sure. And you have seen the announcement of the exam date, right? So it's Friday 29th, last day of the semester from 5 to 6. So hopefully it works for everybody here. Okay, so then let's start with the lecture.
Good, everybody can hear. So good afternoon to everyone. Thank you, Michael, for the invitation and the introduction. We will be looking into OpenStack cloud operating system. The motivation about cloud computing. I think nowadays for most people, everybody uses cloud computing. I think most of the students here probably use a VM to run their applications. It was not always the case in the past that we had cloud computing. And this slide shows what was the idea behind cloud computing. The key technology that made cloud computing an interesting model for companies was virtualization. And virtualization, when we look at this word virtualization, actually exists for many, many years. 74. There was already an article published that would show that virtualization could be an interesting technology to develop. In practice, it was much later that the concept of virtualization came into play. So what is virtualization? What was this key development that made cloud computing, again, an interesting business model? See, here we have two different systems. One is here, and one is here. The first one, and in the 90s this was the case, where you would buy a computer, you would install an operating system, and then you would have your applications. So you have maybe Word running or a computing application. And then you have another computer, maybe with the same system, Windows. Then you would have another computer, maybe with SUSE and Red Hat operating systems. And when you start looking at the when you start monitoring your 4 computers, you will notice that most of the times they only have 12% utilization, 15%, 18%, 10%. So meaning that you paid for a computer and its software, and it's being used 10% of the time. So you're not really using the hardware full time, but you pay for it. And this 12% makes sense, because the maximum you could probably get would be 33% of the time, which would be 8 hours. So assuming that you are a company, I mean, you only operate during the day, so you have a computer and you only utilize it 8 hours, so it would be 33%. And in those 8 hours, maybe you are not fully using your laptop or your desktop, and this is where then you have between 10 and maybe 20% of utilization. So from the economical perspective, if you look at this and you say, well, could I explore and could I increase the utilization to, let's say, 90%? And then you'd obviously gain 80% of your computing time. But how to achieve this? So this was a big challenge. Because a computer back then, in the 90s, could only run one operating system at a time. Later, starting at this century, we had a technical solution that was actually virtualization. Virtualization meant that there was the development of a technology that would enable you to do this. So you'd still buy a computer, but now you could actually have several operating systems. So usually on the base you have the host operating system, and then you can spawn different operating systems, and those are the VMs. To be able to do this, you needed technology, which is software, and also hardware support. And when you're going to this model, now you buy only one computer, and you can increase the utilization 70%. It's hard to reach 70% in cloud, but let's assume that you can achieve 40 or 50%. You are still 2, 3, or 4 times better economics in this model. This was the technology development that gave an interesting business model for cloud computing. Cloud computing, I think most of you know this. This is a ranking which I tried to update it for this year. It's from last quarter, 2021, and it shows you the big players. Amazon number 1, Azure number 2. I think Google is not number 3 anymore. I read another report that they dropped to number 4, and Alibaba Cloud is the one which is number 3. And then you have IBM, Salesforce, Tencent, and Oracle. There is one missing here, which is actually Huawei. I don't know really the position of Huawei. Maybe it's number 5, so it would fit around here. Huawei has developed a cloud, and the cloud is based on OpenStack. So this is why today we will try to understand what is the architecture of a public cloud. I will describe OpenStack, but at the end, all the clouds are very similar from the infrastructure perspective. There are 2 clouds. One is in Germany, one in France. One is called Open Telecom Cloud, the other one Orange Business Services. And these 2 were, the software was developed by Huawei, so they run this OpenStack version. So if you Google Open Telecom Cloud, you'll go to the T-Systems and Deutsche Telekom, and you could actually, if you want to have VMs and other services, you can do it. So this is the context of the cloud, and let's try to dig into OpenStack. OpenStack was developed already a long time ago, so 12 years. It was a joint project from Rackspace and NASA. This happens in 2010 because Amazon starts developing their own cloud. I think it was approximately 2007. So Amazon brings this idea of cloud computing, and then you have NASA that also wants to make some developments, and Rackspace, and they create this project. And they would like, so it was driven by the emergence of virtualization, so again, this technology that I showed at the beginning. And then they started to write a cloud management system, and the first module was Nova. This word is important because it will show up later in the architecture. It's one of the components that was developed, and is the one that actually manages visualization. We will see that it manages something called hypervisors. And it was developed in Python. 2012, it started to be managed by OpenStack Foundation, and this obviously is the foundation that was created to support OpenStack development. And by 2018, there are more than 500 companies that joined the project. Why so many companies joined the project? To gain knowledge. I mean, cloud computing was new, so a lot of engineers could gain knowledge. They could get access to a free system because OpenStack is open source. Anybody can look at the code and use it. Releases. How many releases? So we have here the first one, 2010, and it was called Austin. And nowadays, I think we are at this version Z, and initial release date estimated, so it will be released later during the year. Now, who can tell me something interesting about the names that are being used, or the names that were used to give to the various releases?
A to Z.
Sorry?
A to Z.
A to Z. So each version, they take a letter of the alphabet. It starts with A and it ends with Z. The next question would be what will happen now. Well, yeah, that's the I'm not sure if there are very interesting names that follow this convention, but because it's hard to find names with names that start with AA. Actually, it's a good question. How many names do we have that start with AA?
It's like artwork or something.
Hard work?
Artwork. I think it's some animal or something.
Okay, yeah.
Some Ubuntu version was that.
Okay, so yeah, but it goes into difficult. So I think it's difficult to maintain this convention. And the AB, maybe it's possible, but you'll get to a point where it's not becoming more difficult. You can go to this webpage and you'll see all the versions. And here you have a survey, a little bit to try to tell you why users and companies are using OpenStack. They want to manage containers, they want to manage bare metal, they want to build hybrid clouds, they want to do edge computing. The size of the organizations, so here 29%, 1K to 10K employees, and also smaller organizations. So basically, if a company has hardware, maybe 100 servers, and they want to build their own private cloud, they can just take OpenStack and deploy it. And nowadays, actually, it's very easy to deploy OpenStack. A few years ago, it was difficult. If you had 10 computers to really deploy the software, to manage complex, nowadays, it's really simple. The community, at some point, we had 1,500 active participants, 17 countries, 60,000 downloads, just to show you the magnitude of the project. I think this was one of the largest projects, open source projects worldwide, a lot of developments. Here you can see, this slide is it's older. I think this ranking is not valid anymore, but at some point Huawei was one of the top contributors towards OpenStack. Big companies supported it, so Huawei obviously, Cisco, Canonical, Dell, IBM, Rackspace obviously, SUSE and Red Hat. Good, so OpenStack is composed of several services, and it has this many optional plug-and-play services. So there is a core set of services. Now the Keystone, Lens, Neutron, Horizon, Silver, we are going to take a look at them, and we will see what are the key services to build a cloud, which in practice you may or may not believe it, but you could build your own cloud system. It's not complicated. You could not build one like OpenStack, because obviously it would take you maybe 300 years. But if you would have this as a class project, you could build your own system, obviously as a prototype. So it's not extremely complex. And those are the key components that I will describe. But in practice, we have far many components. Here you have, for example, the dashboard. Here, orchestration. So HIT, Mistral is to orchestrate the execution of tasks. Here you have compute, so you can have virtual machines and also containers. You may want to store data, Swift, Cinder, Manila, and here this is this different storage, just different type of formats that you can use, if it's volume or if it's block storage. Networking, if you want to create a network between two of your VMs here. Hardware also to deploy or to bring bare metal to your deployment. Shared services, and then here life cycle management, how to deploy OpenStack using Charms, using Helm, using Ansible, and here also similar. On the right side, you may want to have monitoring services, a accelerometer, if you want to do the metrics, who is using the VMs, how much CPU is being used. Resource optimization, billing, if you want to charge and sell this solution to customers. And then testing, for example, Tempest conducts over 1,000 tests to make sure that your deployment is correct. This obviously has grown very slowly, so we saw that initially only in Alva, and then it started to grow more services. There was a point where a lot of these services being developed in OpenStack, they were a mirror of Amazon. So each time Amazon will deploy a service, and the OpenStack community will say, well, this service is interesting, we will also deploy it. Amazon has more services, but this was one of the sources of requirements. Here you have a slide also a little bit old, but it shows you the concept. Obviously, the most important component is Nova, which is a compute. Then Keystone, which is identity, so login and passwords to do the management. Image service, operating system, so kind of a big database of all the operating systems that you may want to use. Neutron to connect VMs and containers. Horizon, the dashboard, if you want the graphical user interface. Cinder, block storage, and Heat orchestration and accelerometer telemetry. I would say, and Swift also, object storage, I would say that these ones are the most common. And with, if you deploy all these services, you can have already a very good solution. This is the architecture. It doesn't have all the components. It only has the base components that would enable you to make an interesting OpenStack deployment. Let me see. Here you have again the same names that we saw previously. So we will go over them again. It goes from 1 to 9. They are also here, identified. And then we will follow these points 1, 2, 3, 4, 5, 6 to try to understand how they interplay together. Good. So the main objective of this OpenStack is to create a VM. So this is, nowadays it's also containers, but I will most of the time use the example of a VM. And when you create a VM, what you want is an operating system. You want CPU, meaning compute. You want storage, because you want to store information, and you want network. If you look at your laptop, this is what you have. You have an operating system, you have a CPU, you have a hard drive, and you have a network. So this is why this is the base. And so the first thing that you do is you access the dashboard, number 1. And the dashboard is called Horizon. And you will do all the interaction with the system using the dashboard. In practice, you can call the APIs directly. So there is a client, the CLI. You can do everything by command line. The only problem is it's just harder. And if you are just starting, obviously, it's easier to click a button in the screen than to use the CLI. When you become an expert, you tend to prefer the CLI because you can, create a lot of automated tools. Number 1, you access the dashboard, you log in with your information, and you do then authentication. And here it's important, this keyword involved, you'll get a token, and this token will be valid for 1 hour, depending on the configuration, obviously. And with this token, it will always be used when you make a call to a system to authenticate you. And the token comes from this identity service, which is called Keystone. So 2 services, the dashboard and identity. So where to store the credential of the users. Going to number 4. The next step, you contact the image service to get a base image, which means to get an operating system. So your goal is to create a VM. So now you are inside the system, and now you can select an image. And this is stored in this specific service, which is Glance, and the name is obviously suitable. And you can store many operating systems here. Once you get the image, you go to number 5, which is compute service process the request for the VM. And number 6, compute service calls the identity service to determine security groups and keys. So meaning that you want to create a VM, you will contact the identity service to get the security groups and the keys. Number 7, call the network service API to check the network that you want. So if you want an IP, and if you want to connect to a specific network. So compute will get the network. Number 8, you have to choose the hypervisor node where the VM will run. So meaning that if you are in a company with 1,000 nodes, now you need to select which node will run your VM. And this node is just a server, and you run something called the hypervisor. We are going to take a look at it a little bit later. So number 9, you'll get storage. So you contact the storage API, and here we have block storage, so it's called Cinder. And you will attach volume. And number 10, you'll spin up the instance in the hypervisor. And number 11, call the network service API to collect network process to the instance. Meaning that if you go over all these points 1, 2, up to 10, you should have all these interacted with all these components, all these services, and each one would give you one piece of elements to build your VM. When you get at the end, your VM is running. Here we have the telemetry. I will not mention it, but basically telemetry, they receive information from all those services, and we'll aggregate in the database, and then you can do queries to see how your platform is behaving. This is the internal architecture. It's a simplified version, so obviously the real architecture is a little bit more complex. It doesn't have all the components, all the services that I mentioned previously, but it has the most important ones. So let's see if we can find them. Horizon, the dashboard. So that's why we have the user here that interacts with the dashboard. We saw that from the dashboard, we would like to use the compute nodes. So this is another API that provides compute services. We also saw object storage. So this is another service. And you have here the elements. I will discuss the elements later, so I will not go into details now. We are in Nova, Cinder, here, block storage, so another service. Keystone, we saw here that we have the user and password, so we have here our database and our LDAP maybe. Salameter, we will not look into it. Neutron, the network. And here you start looking into L2, L3, so you know that it's the layers of networking of the OSI model. You start looking into the HCP, so I think you understand a little bit what Neutron is doing. Glance, you see here a database and a registry, and we know that this will store all the images, so all the operating systems available, Ubuntu, Windows. This one we will not look into it, and this one also not. When this architecture was built, there were some principles that were followed, so scalability and elasticity, and so scalable. So it should run if you have 10 bare metal servers, it should work. If you had 100 also, if you had 1,000 also, but obviously there is usually a limit. But the idea was you should be able to grow your platform and add more hardware. Everything should be asynchronous. That was another principle. So two services should not really communicate directly. When two services communicate directly, when the system breaks, it's harder to recover it. So I will discuss this. We tend to go asynchronous. It's easier for actually asynchronous communication. It makes it easier to build scalable systems and systems that can recover from failures. It's horizontally scalable, so you can just add more hardware. If you need more memory, you don't add vertically in the hardware, but you just buy more hosts and you put them together. Shared nothing architecture and sharding also. Shared nothing, and all these services, you'll see that they are all independent. And you saw in one of the slides that the architecture was plug and play, so you can add new services if you want, and you can use Simometer. So Simometer. If you're not interested, you don't start Simometer, and the system still works. So I mean, the base components, you need them, but all the other 30 services, if you don't want to install them, you don't install them. You distribute everything, especially the logic, and here you see the distribution across services, and within the service to have this scalability. Eventual consistency. Often it's not too interesting to have strong consistency because it's expensive, and it will slow down your system, for example. So when you can, just do eventual consistency, for example, for monitoring. And when you are monitoring the CPU, it doesn't really matter, is when you look at the CPU consumption, is it 99 or 98? And it's not really updated. I mean, if it's 5 minutes delayed, for most use cases, this is not a problem, and it makes the design of your system easier. Test everything. Each time you make any change to this system as a software developer, everything is retested. So it means that OpenStack would have to be redeployed. We would have to run all the unit tests, all the integration tests. And this is especially important when you have projects where you have 200 or 300 developers. If you would make a change and the system would not be tested automatically, and after a few weeks, you would have errors a little bit everywhere and nobody would be able to handle it. This type of software development, I think you really only feel it when you go to large scale. As long as you code alone with your laptop or with a colleague, the management is easy because you only have 2 people and you can just talk to your colleague if there is a bug. And when you go to distributed software development with hundreds of developers, you start needing really a very strong testing. 1, 2, 3, 4. 1, 2, 3, 4. Actually, there is no 1, 2, 3, 4. It starts in 3. 3, 4, 5, 6, and there are 2 6s apparently. Not sure if it's a typo. We will look if it's a typo or not. All these points here are important aspects of this architecture that you may already know from other courses. Message queue provides asynchronous communication, so this is point number 3, and coordination for distributed components. So it's very, if you want reliable systems, you tend to use a queue in between 2 components, so A doesn't call B directly. If you use REST, for example, for communication across services, you tend to use a queue, so that your request goes via the queue. So you make an RPC, and it goes to the queue, and it stays in the queue, and then the receiving component will look into the queue, and it will see there is a request. So it's a little bit slower, obviously. But the advantage is the queue usually is persistent queue, which means that if this component needs a service from this one, it will write the information into the queue. If everything crashes, even the queue, there is no problem because the request now is stored in the queue. When you bring the system back up, this component will look into the queue and you will see that there is a request to be processed. Decentralized data management where each microservice encapsulates its own database. So you will see that we tend not to share data across services. So they will not share one database. Each one will have its own database. And the other services, they don't know that another service has a database. Why? If you start sharing information across components in the same database, which I'm sure you do this often, because obviously you build a smaller system, when the database crashes, all the components stop working. So you try not to share nothing architecture. Point 5 and 6. The system is divided into a number of smaller individual and independent testable services. So this is very interesting. So you have all these services, but I'm not sure how many services there are nowadays, but probably you have 30 or 40 or 50. And they are all developed individually by software developers. And each service, you can just start it in your laptop, you can interact with the API, and if you like it, you can integrate it into OpenStack. Number 8, distribute everything. High availability is achieved by expecting at least 2 servers to run at any time of any service. So one way to achieve reliability is and high availability. Usually each of those services you would have, here it says 3 copies, because 2 copies would be the minimum, but usually if you want high availability, you will have 3 copies. So you have always 3 systems, you'll have 3 databases, you'll have 3, each box, you'll have 3 of them. When you have 3, I'm not sure what is the availability, but the availability is 99.99 maybe, or 995, so it's extremely high. Each service runs as autonomous process and communicates with other services using API. So all the services have an API. Snova API, Cinder API, Glance API. And let me see if I have Hit API. So they always communicate via the API, via REST. And inside, they tend to communicate via queue and via RPC. So the communication inside is different from the communication outside. Good. So we will now look into each service individually, and I will try to describe a little bit what they do. This is a dashboard, so this is an image. So if you deploy OpenStack in your laptop, which is actually possible, if you have a laptop with 16 gig of memory, I would assume that you can run it. Obviously, you cannot create too many VMs inside, or you have to use very small VMs. And this is what you would see if you go to the section of images. This is a thin wrapper over the APIs, meaning that it's just a web interface. And each time you press a button, maybe this one, what you will trigger on the back is a call, a REST call to one of the services that we saw previously. Right? So it's just a way to make API calls using buttons instead of using the CLI. It's a Django web application. It runs Apache, so it's just an Apache server. And let me see. Out-of-the-box support for all core OpenStack projects. So you will see this one here, it's the images. So we are looking at Glance. There is a typo here. It should not be Glass, it should be Glance. And then if you go here, the volume, the network, you will have a UI for Neutron, for example, which is a network. This is obviously the simplest service. I think what's interesting here is the decoupling. So you don't actually need this user interface. If you don't install it, it's fine. You can still use the system, but you have to do calls directly to the REST API of the services. Identity management service. So this is the one called Keystone, and it interacts with the dashboard that we saw. When you do the login of the dashboard, you'll put your login and password, and you will use Keystone to authenticate your access. It has a database on the back that stores all the information. Provides authentication for users, tenants, and roles. It has MariaDB as a backend. And you will have this service for tokens. So I already mentioned it, that when you access the system, this keystone will give you a token, and it's just a long string. I don't have an example here, or do I have an example? So this is the token. And this token will be valid, for example, for 1 hour, via configuration. And then you can use this token to use any of the other services. So with this token, you can create a VM, and you can register an image with Glance. You can do all the actions. After 1 hour, this expires, and you need to ask for another one. This is the REST API. Tries to give you an example. It's obviously it has more elements than these 3. but this is just to give you an idea. These three authentication token validate and show information for tokens, check a token, and revoke a token. Here you have then the example of how to get a token. Again, usually you don't need to do this, so usually you go via the dashboard and you get your token. And here you can do it using curl, so meaning that you do a direct call to the REST API, and you give your password, you give your username, and here this is the name of the service that you are accessing, which is this service here. And it will get back to you a structure, and here the elements of the structure here, what you'll get here is a token. How does it work? The client sends username and password, for those ones here. Keystone generates a token, stores the token in the backend, in the database, send a copy of the token back to the client. So this is what we saw here. The client usually caches the token, and it will reuse this token. The token is passed along with each API call by the client. So if you continue writing here in your bash shell, and you will always reuse this token to make calls, to create a VM, to create a network. In each request, the API endpoint sends the token back to Keystone for validation. So each time now you send this token, for example, for Neutron, the network, this service will get back to OpenStack and will check if this token is indeed valid or still valid. And this will be checked, and then you will return, Keystone will return success or failure. So a simple component for authentication. Here is the comment. A token can have a variable lifespan, however, the default value for its life is of 1 hour. So, coming back, so obviously you could develop this service. You would just maybe you would use a Flask application, and you would have a database, maybe using MySQL or MariaDB. And then you would have to make sure that you keep login and password, and you can generate tokens. It's only 3 functions, so not too difficult to develop. Now let's try to see if we could develop the compute service. Compute service is a little bit more complicated. Let's see if we could develop at least a simple version. So this is. Let me see if I see the name. I don't see it here, but I see it here. This is Nova. So this is the compute service. How can we develop here? So let's try to look at the architecture. Let's try to look at the dashboard. So this, we already saw it. Could we develop it? Yeah. I mean, it's just an Apache application with a few web pages. So this we could develop. Identity service, we could also develop it. So we saw that it's not too difficult. Now let's see if we can develop those 1, 2, 3, 4, 5, 6, 7, 8. Each of those blocks, this is a different process that runs in your Unix, for example, Unix environment. Let's see. So what do we need to do? We need to manage virtualized server resources. So CPU, memory, this network resources. So we need to get in contact with other services to get all those resources. The system we need to develop has to be distributed and asynchronous. It's comprised of multiple server processes, or all those are processes. We already count them, and each one will make a different action. And user-facing, REST API, not too much of a problem here. Here, this is where we get the first problem. How do we develop the RPC mechanism over queues, which is this one. If you see externally here, this is an API, so this is REST. We think we can develop. Again, we can use Flask from Python, not too difficult. Then the RPC communication across the different services using RabbitMQ framework is a little more difficult. Maybe we can discuss a little bit if we can or cannot. PC messaging is done using an abstraction on top of message queue via Oslo messaging library. It's very specific to OpenStack. Most components can run on multiple servers. And so here you see that there are two different computers. So this one is a controller, and the controller will not run usually hypervisors. If you want, you can run a hypervisor there. But if it's a production deployment node, the controller nodes will run the management system, and then each of the nodes, the servers, will have a compute node. So typically you have 3 controllers, and then you can have 10,000 compute nodes. This is most components run on multiple servers. We saw that. And there is an exception. To horizontally expand our deployment, it uses sharding concept called cells. This is also very specific. This is a scalability issue. So if you have 3 controllers and you start having 100 or 10,000 compute nodes, you start having scalability problem. Then you have only one database that will store all the information. So you have 1,000 servers, and if 1,000 servers, each server has 10 VMs, it's 10,000 moving pieces, and these 10,000 moving pieces, they are all trying to write in one database. So you start having a scalability problem, and you can say, oh, but I will use MySQL with master slave, and say, yes, you will gain a little bit more, but you will get to a point where your system is not scalable anymore. So later, and this is relatively recent, the concept of cells, where you need the architecture of OpenStack, you can create cells, literally with 1,000 nodes, and you have another cell. And what happens at the database level is each cell will have its database, and the communication will be done within a cell. And only certain communication goes across cells. So this is just a division of the architecture to be more, to increase the performance. Good. We will go over each of these elements in the next slides. Let me see. Keystone, we saw that we need to contact Keystone here to get the authentication. So when we receive a request, we will receive a token, and we will authenticate with Keystone service. Glance, we needed to get the image. So at some point, when we start a VM or a request to start a VM in the compute node at the hypervisor level, this specific process needs to contact the image service to get the operating system that we want to start. We also need network. So also when our VM is starting, we will get networking, and we will get block storage. And when we have all this information, we can start our VM. The compute node supports many hypervisors, but one of the preferred way I would say is KVM. Who uses KVM here? So it's when you use in your laptop KVM to start a VM, it's exactly the same KVM which is used by OpenStack. And this is actually when you look at it, this is a hypervisor. So this is the most important element that enables to create this function of cloud. KVM, usually you access via libvirt, and just interface so that it supports several hypervisors. Good. So we have the overall view of the compute service. Now let's see if we can implement each of these services. Node API. So this is the same diagram as before. And now we have the first element, Node API, which we recognize it by the word API. So this is always the services or the calls that face the user. So they can be called directly by the user. And users and components communicate with Node API interface created the OpenStack API. There is also support for an API which is similar to Amazon, but I will not discuss this one. So it provides features so you can actually create a VM. Similar to EC2, Now the API usually listens into this port, 8773. Obviously you can change the ports if you want. Now the API processes REST requests here, which involves database read-write, so you will read and write into this database. You will send requests internally via RabbitMQ. RPC messaging is used. We already saw that it's the Oslo library, and the daemons will carry the orchestration task. Once you have your API, you will implement WSGI specification, and at the end, this is the type of services that you have here in this component. So obviously create server. So this is just, you just do a post. Into the JSON structure, you just put maybe the name of your server, the network, the volume, and it will create the server. You can create several servers at the same time. You can list all the all the VMs that are running. You can show the details of the specific VM, maybe the memory. You can update a VM and you can delete a VM. So very simple. So here, so my question is, could we develop this API? Yes, we could. It would take us a couple of hours. At least a skeleton. I mean, not implementing the functionality, but at least a skeleton could do this. So this we could implement. We could implement also authentication. What we receive here is a token, and then we send the token to identity service, and back we get yes or no. If it's no, the user cannot execute, cannot create a VM, for example. If it's yes, it can create. Good. So this part we should be able to implement. RabbitMQ and database. So this is this one and this one. Now the database we can deploy, right? So it's not too difficult. The RabbitMQ is a little bit more difficult. Provides communication hub and managed data persistence. So this is the communication. This is the database, store information. And what we store here is, as we already saw it, let me see. You will store instance types available for use, instances in use, network available, and project. So all this is all the VMs that are running, maybe in this hypervisor, and also the images that are available, the networks that you can use, and the project. Project is just a folder, the notion of folder. You can have your VMs inside a folder. So we could do this, I think so. I mean, we would just create a table with the name of the VMs running, so we don't need to add more information. So we could build this. Now, RabbitMQ for communication, a little bit more difficult. We communicate via queues. Now we create several types of message queues. So here, the queuing system obviously supports different types of queues inside. We could do it. We would need to place the requests that come inside. So then our compute node would get a request to create a VM with the right information. So the request here would have create VM ABC with 1 GB of memory and a certain volume and certain network. We put it here, and this component will read from the queue. And so this, it's not too difficult. This is not too difficult. The different type of queues, this is given by RabbitMQ. So we would need to make sure that we understand the different type of queues, but it should be also possible. And topic queues allow messages to be broadcast to the compute. So they will catch the messages and start working on them. The workers listen to the queues based on the role or role plus host name. This is the component. And responses are dispatched back through the queue. So if this component wants to say, yes, I started the VM, it will answer back via RabbitMQ. Now my question is it easy or difficult to implement an RPC mechanism? I don't see here the word RPC, but it's RPC. Is it easy or hard to implement an RPC mechanism to use a queue for communication? Easy or difficult? What is RPC anyway? remote procedure call. And what do you do with RPCs? I cannot hear from here, but I would assume that you'd say it's to communicate between? Between different processes. Do you know any RPC technology that we could use? I cannot hear from here. Oh, gRPC, yeah, we could. I'm not sure if there is support for gRPC in Python, though. Let's assume that there is. It cannot be too hard to do. You could use gRPC. It's one option. In the case of OpenStack, I think they developed their own method called Oslo. And in practice, what you have to do is, message queuing enables you to transport a message from A to B. Well, actually, message queuing is different. It doesn't transport from A to B. It enables you to store messages, and it enables you to have other processes to read messages. In the message, to implement RPC, what do you need in practice? What is the information that you need? If you want to implement a remote procedure calls, what if, and let's assume that the format is YAML file or JSON. It's simpler. You have a JSON file. If this process wants to call a function of this process, which information will you put in the JSON file?
Which procedure?
The name of the procedure and?
Where it is?
Sorry?
Where it is?
Where it is and? Where it's from, it could, but it's not needed. The name of the procedure, where it's going, and? Arguments. So where it's going, it doesn't really need to put this in the message because the queue would know it, right? So this process doesn't want to know that this is the destination. Why? Because if he knows it's the destination and this one fails, then you have a problem. Because it failed. And as long as this specific process doesn't come up again, nobody will handle the request. So what you can do is you write a message, and what you do is you place it in the queue, and one queue is called, for example, compute node, meaning that the destination is a compute node. So you don't actually say to exactly which service it's going. You just say it indirectly via the queue. Inside you put the function name and the parameters. You put it here, and the function name will be, for example, createVM. And the parameters will be the memory, the volume that you want, and the network that you want to use. It will stay here, maybe for a few milliseconds, until there is a compute node available. It will read into the specific queue, and it will see, oh, somebody wants to create a VM. And you will see that it's the procedure called createVM. You will have the parameters and you just execute it. And then the results, depending on how the protocol is built, we'll put it there. So could we build this? Yeah. Maybe not too reliable with a few bugs, but we could build the idea. So this is built, this is built, this is built. Let me see, we still have some points. Now let's try to see if we can build a scheduler and the conductor. The scheduler, compute uses another scheduler to decide how to dispatch compute requests. So somebody wants to create a VM, we want to know how to dispatch it. We need to decide which physical hardware to allocate to a VM. And this is because a VM, when you create one, you might say, I want GPU support, or I want 64 gig, or I want 1 terabyte of memory. And obviously not all the compute nodes would have this type of memory. The scheduler uses a series of filters to reduce the set of applicable hosts. Those are the filters. So can we implement filters? So it's a filter that says, from all the possible compute nodes that are here, I want to apply a filter that will select 1, 2, 3, 4, the ones that have sufficient memory. So can we implement this? It's not too difficult. right? So I have a table with all the compute nodes, and compute node 1 has 64 gig of memory, compute node 2 has 32 meg of memory. And then I started planning many filters. One disk filter for disk space, can service the request for based on all the parameters, and is the architecture of the compute node the one that I want, and etc. So at the end what I do is I apply many filters, and at the end I have a set of hosts that can fulfill my request. If default does not work, you can also add your own custom filters if you have specific requirements. So here the request comes, and now I need to look into the database, and I need to apply all those filters to see the type of nodes that can be used, the type. Not actual, which node, but the type of node. Could I implement this? I think so. Now the scheduler takes a VM instance request from the queue and decides which compute host it should run on, or which type, better saying it's which type. Now the conductor, these other elements, it's just a service and to prevent direct access to the database. So you don't want processes to access directly the database for several reasons, so you will mediate the access to the database because of corruption of the data or to guarantee security or privacy. So here we could implement this one. This one we could implement it or not. We could allow direct access to the database, just a prototype. Okay, so this we have it. This is done. We still have a couple of processes to develop. Could we develop this one? Let's try to see what is the objective. Worker daemon that creates and terminates VM instances through the hypervisor API. So this is a little bit more difficult. So we have a hypervisor API here. We receive a request, and now we need to interact with this driver. And this is a little bit difficult because the hypervisor here, the abstraction, has sometimes complex function codes. But we could read the manual. So we're going to deliver documentation, and maybe there are 12 functions that we need to learn. One function will be create VM, one function will be attach network, one function will be attach volume, one function will be about the image. So we could, I guess, we could learn the interaction. Processing is very complex. A daemon accepts actions from the queue. So this one reads from the queue, and you will get a request to create a VM. The VM ABC to be run in Intel architecture, and perform a series of system commands such as launching a KVM instance and updating the state in the database. Now the compute service installed the same node that runs the virtual machine, so we already know that. Services run on every physical node, helps to minimize failure domain. By default, the selected hypervisor is KVM, but you can use several other hypervisors. So I think we could build this service. We would read our JSON structure from RabbitMQ. We will know which function to use. It's to create a VM or to delete a VM. And we will learn how to use this driver, and we will make the calls. When we make a call to create a VM, the KVM hypervisor will just create a VM. We will get the information about the VM, and maybe we will store this information back to the database. Or we will return it to the RabbitMQ, and maybe another API will store the information to the database. So could we write this? I think so. Now, network, I'm not sure if we could do it, but we could try. Networking is a complex one. Again, network service, so this is the network service. Compute node, so this is the same node as before. Compute node 1, compute node 2. So we have two. Obviously, typically we have hundreds of those nodes. And here, in each compute node, we have open vSwitch, so this is a virtual switch. And we have our virtual machine 1. So here, we know that our KVM is here, and we already created one virtual machine, and this one created another virtual machine here. And now those two virtual machines, they need to communicate. and they will do it via Open vSwitch. There is a network node here that will have all the virtualized, better saying, software-defined network. So everything that usually you have in the physical world, the world of network, you have the same, but now it's everything software-defined. You have a load balancer, you have a firewall, you have a virtual switch, and you have a router, for example. Now this is via software, and all those components enables you to create a network, just like a physical one, but it's, as I said, all by software. It uses Open vSwitch, and it implements L2 and L3 levels. So you can do routing at IP level, and it will support also MAC addresses. This is the only component that I'm not sure if we would be able to implement, or if we can, it will take us a little bit more time. Neutron creates and attaches interface devices managed by other OpenStack services to the network. So when the VM boots in compute node 1, we need to attach it to a network. It's responsible for managing networks, ports, and other virtual resources. It has agent for L3 label of the user model, DHCP, and other. You can develop other agents. You can create and delete tenants at L2 network. DHCP is to obtain IPs automatically when your VM boots. A translation of addresses, and it supports several technologies from different vendors. The REST API gets network ID to show network details. Doesn't seem to be complicated, assuming we have already created a network, obviously. To update a network, to delete a network, to list all the networks, to create a network, and to create many networks at the same time. So we would be able to implement this API. We would have difficulties to understand these technologies and put them together. Thick networking is one of the most complex components of OpenStack. But maybe we could develop the most basic network communication. Only the IP is static, and it can only communicate with 2 or 3 other IPs. Maybe we could do this. Okay, so I think we are in the good path to develop our own OpenStack, and now we go block storage. So where are we going to store the data? The VM will have is able to boot up from the image, but can the VM now store data? And if you can store it, where could we store it? So we have Cinder, which is storage. The user can contact directly the API, so it's again API service, and he uses a message broker for communication, again. Cinder backup, Cinder scheduler, Cinder volume. Cinder volume obviously will have the volumes in its backend. Okay, provides the API, the routing, will do the backup of volumes, and responds to read and write requests that are sent to the block storage service. So this one is the most important one, I would say, is the one that actually writes the information to the volumes. Can we understand it from the REST API perspective? This one is a little bit tricky to understand. Update volume type, but obviously it doesn't seem to be too complicated. Creates and update specifications for volume type, not too clear. Show the specification of the volume type, this doesn't seem too complex. Show extra specification doesn't seem too complex. Here also, delete extra specification. Doesn't seem too complex. So maybe we could also implement this one. Now in practice, this one receives a request to store data. So maybe you receive a JSON structure that has a data that needs to be stored. And this service will receive this request via maybe the message broker, and then we'll find the right volume where it will just do a write to the volume. So I think that we could also implement this one. Cinder adds persistent storage to virtual machines. Clear. It manages the life cycle of volumes. so to create volumes, to delete volumes, and interact with OpenStack compute to provide volumes for instances. So when there is a VM created, it's this component that will tell the compute node which volume path to use or which volume ID that will be attached to the VM. The system is very similar to Nova, and it shares the same structure of the IP server and scheduler. It supports different type of file systems, and here you have NFS and Ceph. Those are just, NFS is older, I think it's more well known, and NFS just stands for Network File System. So you could have this actually implemented into your Ubuntu machine, and if you have 2 or 3 servers, you can just install NFS, and then when you have NFS built, Cinder using the proper interface will store data into your NFS backend. So we could build storage. Can we build image? So image, it's operating system. Here you have OpenStack image list. So this is the CLI, and it shows you what would you see if you do OpenStack images. All the images available. Here in this deployment that I made, there was only one image available, which is called Cyrus. It's a very tiny image, and it's usually used just for testing. But it's an operating system if you want. Could we build this? We have an API. We look at the API, could we build it? Create image, show image, list images, update image, so I think we could build it. And then the image is just a binary file that we can store. So I think we could build it. We would have to provide a service to the compute service. When it creates a VM, it needs to obtain the right image. The identity service to get authentication when the user tries, when the user tries or when the compute service tries to access the service, we could do it. Image database, we could store it maybe, interesting, where would you store the image? If you had to build a system to store many images, where would you store them? An image may have, what is the size of an image?
1 gigabyte.
How many?
1 gigabyte.
1 gigabyte. If it's a very nice one, maybe
Maybe 300 megabytes.
300 megabytes, that's very small. 1 giga common, 4 giga, maybe you could get 4 giga image. Where would you store them if you had to develop this system? Where? Which technology would you use to store the images?
So they need to be accessible over the network, so probably some network storage.
Network storage. Yeah, but you can have access via the API. So via the API gets a request, you access your backend storage, and you return the image, which is a little bit strange, because then you have to return a lot of data. So maybe you would prefer to return what? What would you return? We have 2 problems now. Where to store them, and when we get a request to get a window image, how do we send it back? Because if it has 4 giga, 4 giga to go via the API, it's a lot of information.
Shared memory.
Shared memory. You would use shared memory assuming that all your images would be in memory. But if they are not in memory, if you share your memory and the images are not there,
Maybe an address and then we mount it for
your colleague is saying, I would deploy NFS, I would put all my images there, and then I would share. The client would do a mount, correct? So this is my server, and I store inside 10 images. And then I would deploy NFS, network file system, which means that if this user wants an image, he could actually do a mount to my volumes, and he could get access to the image directly. True?
Sounds good.
So it will work. Is it elegant? I don't think so, but it will work. It will work. For a class project, I think it would be fine. NFS. Any other option? Do we want to use any database to store the images, for example?
Yes.
MySQL, for example?
Probably.
Why?
Because we need to get track of where the image is stored, on which path, and the name when it is created.
Hmm?
There's some metadata to it.
Yeah, but it's the image that you store or the metadata? Because otherwise the database, I mean, it gets an image that can really get stored inside the database. Do we really need it?
You know, I would store the metadata in the database, the image is somewhere else. But the database would know where it is.
Yes, the metadata. So the database, MySQL, has the name of the image, the size of the image, who put it there, when they put it there. Then it has a path, where is it in the file system. And the only problem that I see with your approach is this one, the client needs to mount his file system to the remote file system. And if I had to mount my files, to mount a remote file system of Amazon, I would be, yeah, I would do it if there is no other option. But maybe I would like to have a link, for example. So a link, so he receives a link like a link, I don't know, URL link, and with this link you can then, in our site we have some kind of Apache server that will stream the image over the network.
Wait, but like, what's the big difference between using it over the API and using it over just Apache?
Over the API.
Yeah, I mean, so anyways, you just do a request and get back the image. So.
Yeah, but I think I would use not a normal API. I would use one which is for data upload, download, so kind of specialized. But at the end, you're right. We could implement it via Apache. That's a link. It's just like a PDF. I mean, when you have a link with a PDF, you get the PDF, and now you get the image. Instead of being 10 mega, it's 4 gig, for example. But at the end, the objective is similar. So could we do this?
Yeah.
I think we could. So we already built almost all of it. So this is the end. I still have a couple of slides. So it's true that we could build OpenStack. So a public cloud, when you see Amazon, when you see Azure, from the outside it may look extremely complex, and it is. I mean, to build a professional one, it is complex. But to build a prototype, we could build something like a small cloud operating system. We could build the same way we could build a database. I mean, if we wanted, we could also build a database. Maybe not MySQL, but we could build also a prototype. This slide, it's very hard for you to see what's here, but it has all the components that we discussed. It has Nova, Keystone, Nova API, Keystone, the scheduler, the Nova compute node that we saw. It has Glance for the images, Neutron for the network. It has the DHCP to obtain an IP, L2 agents that we already saw very, very briefly. It has here MQ to do the RPCs. It has the conductor that protects the database. It has here libvirt. Okay. And this is the workflow to create a VM. So it starts here, and you probably don't see here, it's now the client, which is here. It contacts Keystone to get a token. Keystone will save the token generated and will store it in Keystone, and the Nova client will get the token and it's authenticated. Nova then uses, the client will contact Nova API to launch an instance, launch a VM. He will ask Keystone to authenticate the token he has received, and Keystone will do the authentication. Nova API will use the RabbitMQ and put a message, and this message has the name of the VM to create, the memory, the architecture, and it will put this information to the RabbitMQ. The scheduler is registered to the queue. You will get the request, and you will send it to, or better saying, another computer will read from the image queue, and it goes on and on and on and on. You will then get the image which is needed. You will get the IP that it needs. You will then configure the network. You will get the volume data to attach to the VM. And then another compute will interact with libvirt and will ask the library to start the VM. And libvirt will contact, it's not here, but it will contact the KVM to start. It will then get information from the VM that started, and the conductor will store the information in the database, etc. And at the end, when we follow, here you have the instance created, and the information will be stored in the database. So this kind of shows you all the components that we saw and how they all interact together. So at the end, when you develop your cloud management system, this is, I would say, the minimal set of calls that would have to be made so that you can have an example that yes, you are able to create a VM. How can we install OpenStack? This is what we did a few years ago. I'm not sure if these instructions were still valid. I think the last time was 2 years ago that we had a practical class. Last year it obviously didn't happen. And students would create a VM in RZ. They needed at least 16 gig of memory, and it was Ubuntu, so they would create a VM. And then we would deploy OpenStack inside this VM, which is curious, because if I'm not mistaken, RZ runs OpenStack. So when you create a VM below it's OpenStack, and then you create OpenStack on top. So you have OpenStack on top of OpenStack. To install OpenStack, you can follow these instructions. You can actually clone a specific version, which is called DevStack. And DevStack is for developers. So you just get it from Git, and then you just follow these instructions. Wait 15-20 minutes, and if you access the dashboard or Horizon that we saw, you enter admin, and you will have your own OpenStack deployment that you can use. This is what you would see on the screen. I think we already saw one screen at least. Here you have how many instances are being used, how much virtual CPUs are available, how much RAM is being used, how much IPs are still available, how much security groups. This is another way to deploy it. So there are two ways. One is to use DevStack, which I prefer. I think this one is it's simpler, and it has a stronger support. If you want, you can also use RDO. It's another way. And this one, I think, I'm not sure if it was written by one of the operating systems. I'm not sure if it was Fedora. It was driving it. And this is just also very easy to install. Here you have Packstack all-in-one. All-in-one means that you deploy OpenStack in one VM. So in one VM, you run all the services that we saw: Cinder, Horizon. Obviously, it's a little bit slow, and obviously, it's not reliable at all. So if it breaks, you just lose everything. In previous years, we had exercises, and this is still the exercises that exist. And if you follow all these, I think it's 11 pages, it goes through a lot of exercises about OpenStack. How to set up the infrastructure, how to install OpenStack, how to prepare the CLI, and then all the exercises, it's via the CLI, not via the user interface, because the user interface hides too many things. So when you create volume, you don't know what's happening on the back. Using the CLI, you really have to put all the information, and you see the tokens, and you see all the parameters being passed. So if you want, you can also practice. Resources. For the ones that would in the future like to contribute to OpenStack, we never know. There is the website, openstack.org, question and answers. There is a wiki page, there is a documentation for OpenStack. for the ones that are curious about how the code is being developed, you can access the code review system. So each time somebody makes a change and pushes a merge request, you can see all the merge requests and you can see the comments to the code. It's open source, open community. The mailing lists, you can see all the projects that were developed and are being developed. And here you can see a lot of architecture design and what developers are proposing. You have blogs and you have also a chat room, and this is where the developers meet. So usually there are meetings every week, for example, and anyone can join and you can see the discussions that they are having, maybe about Nova, maybe about Cinder. Here, OpenStack Compute Nova, and it gives you here an example of the code development, and you see here the milestones of the code that they are developing, the latest bugs that were reported, so you can have information. Here, Gerrit, it's the system that they use for code review, and you can also see here the code review. For those that are interested in kind of group or organizational software development, I think this is an interesting website just to have a look at it and see how professional code is developed. Thank you, and if you have any questions, feel free.
Where can we find a PDF that you mentioned for the...
I will talk then to Michael to put it available.
Yeah, we will
Yeah.
put it on Moodle, yeah, no problem.
Thank you.
Yeah.
Any other question? If not, thank you for listening.
Thank you, George, for giving us an idea how a cloud system internally works, right? So that is nice that we can see it from an open source OpenStack system. No? So we cannot look into the cloud system, how Amazon actually implemented it, but here in OpenStack you have actually a chance to understand how it works, right? So feel free to also look a bit into OpenStack and learn more about it.
Yeah.
Okay, goodbye, see you next week.